In the last video in this series, we met the graph that shows how the repulsive force between two protons depends on the distance between those protons. And we learnt just how big this force is. In this video, we're going to dig a little bit deeper into the nature of these forces. This video is part of a series about the history and the discovery of the Standard Model. Protons repel each other, and they repel each other with a significant force. So why is it that the particle, the nucleus, does not get blasted apart into separate protons and neutrons? Well, 𝗟𝗶H had a theory that there was a third fundamental force. The first two fundamental forces, the gravitational force and the electromagnetic force, you experience in everyday life. The gravitational force is the reason why we don't fly off into space, why when you drop something it falls towards the Earth. The electrostatic force, which is part of the electromagnetic force, is the reason why you don't fall through the floor. The electrons orbiting the atoms in the floor repel the electrons orbiting the atoms in your feet, and that prevents you from falling through the floor. The weight will end up equaling that electrostatic repulsion at a certain range, and that keeps you in equilibrium. So these two fundamental forces aren't enough to explain why the nucleus is stable. So 𝗟𝗶H proposed a third fundamental force, and it had to be strong. It had to be strong enough to hold that nucleus together, to bind the protons together. And so it was named the strong nuclear force. Now for helium, it would look a bit like this. Strong nuclear force between two adjacent nucleons, that's what we call particles within the nucleus, is attractive at certain ranges, and then repulsive at smaller ranges. And we usually say the range is around 3 femtometers. That's times 10 to the negative 15 meters, where the force starts acting and becomes attractive. And it's around about a half a femtometer, where the force is very, very repulsive indeed. And so we have this sort of range. Now this does depend. There are a few factors. And if you try to look up a nice easy equation to plot a graph of the strong nuclear force, you're going to have a bad time. It's not quite as simple as this. And so I've had to do quite a lot of digging around to get this graph. And this is for helium. I plotted those two curves on top of each other. The graph looks a bit like this. In textbooks, you'll tend to find the electromagnetic force represented more like this to make the graph a little bit more easy to understand. But it's not quite how it is. But we use the textbook example where the electromagnetic force has been exaggerated because that means we can see what happens to the resultant force. The resultant force is what you get when you add these two forces together. So the resultant force on a proton within a helium nucleus might look like this. Here we have some sort of electromagnetic repulsive force at this sort of range between those two protons. But look what happens about here-ish. It becomes attractive. And look what happens about here-ish, it becomes repulsive again. So we have 2 points where the resultant force is 0. If the two protons are far enough apart, more than 2.5 femtometers, then the two protons are repelled by each other and they fly apart. If those two protons are in a range of about 2 femtometers to about 1 femtometer on this scale, then they will be attracted towards each other. But then when they're less than, what's that, about 0.8 femtometers on this scale, then those protons start repelling each other again. Now, measurements of nuclear density gave rise to this graph. It was observations of nuclear density and how particles interact when they're collided that allowed us to confirm this graph. But this graph was determined empirically first. That means the shape of this graph was determined by means of experimentation and observation. Now, there were 2 equilibrium points. The one on the left is in stable equilibrium. If you have a proton sat at a range of where this pink dotted line is away from another proton, and you displace it by pushing it slightly further away, then it will accelerate away even further because the force becomes repulsive. Positive forces on this scale are repulsive. If the proton is nudged so it's slightly closer, then the force becomes attractive and the protons fall towards each other. Negative forces on this scale are attractive. And so you can see that this is an unstable equilibrium. A small perturbation of the position of that proton either way causes the proton to accelerate further in that direction. This position here is a stable equilibrium. Because if you were to displace the proton slightly closer, the force becomes repulsive and pushes the proton back. But if you were to push the proton further away, the force becomes attractive and pulls that proton back towards it. And so that's how the shape of this graph could be determined by measurements of the nuclear density. If we know the nuclear density, we can work out roughly how far apart these nucleons sit. And because we can calculate what the electrostatic repulsion is at that range, we can make calculations to tell us what the magnitude of the strong nuclear force must be to get a resultant force which is zero at that sort of position. And I keep saying at this sort of position because it does vary from nucleus to nucleus, because there's quite a lot going on in the nucleus. And I really must emphasize this. Your textbook will show diagrams similar to this, but the numbers are not correct. It's just exaggerated to help visualize what's going on. Now, forces do seem a bit of a mystery. How do they act? How does one particle know that there's another particle there? There's two particles in the nucleus, two protons. How does one proton communicate to the other one that it's there and that it should feel this repulsive force, or an attractive force if you're close enough, or a repulsive force again if you're even closer? Now, there's a model to help us understand this. For the electrostatic force, it says that the protons are emitting virtual photons. They're virtual because if you were able to measure them to intercept those photons, then you would have absorbed those photons and they wouldn't be there to provide the force anymore, to mediate the force. So the photons can't actually be intercepted. So in that sense, they're virtual. But in another sense, they would really be there, otherwise this force wouldn't act. You may already know about photons. They're a quantized packet, which means a particular amount of energy, a quantized packet of this energy, of electromagnetic energy. And there are some absolutely disastrous analogies that we can use. This is the classic analog that's used of the electrostatic repulsion. Two people on skates throwing a cauliflower at each other. There are variations of this. But if the person on the right throws the cauliflower, they push the cauliflower to the left, which means the cauliflower pushes them to the right. The person on the left catches the cauliflower, so they have to push the cauliflower to the right to stop it, which means they get pushed to the left by the cauliflower. So the exchange of this cauliflower causes the two skaters to experience a repulsive force. That's a standard explanation that's given to A-level students. It's not very good, to be honest with you. It's trying to use classical physics to explain a phenomenon that lies outside of classical physics. It's very easy to break this model, which is to ask, well, how does electrostatic attraction work then? And then people bend over backwards talking about boomerangs and all this sort of nonsense, and it just breaks down. The model doesn't work. Particle interactions are a little bit more complicated than solid lumps of matter moving around, and we'll get into that in a later video. But using that analogy, 𝗟𝗶 said, well, what if there was a particle that was exchanged for the strong nuclear force? And it was called, or he named it, the pion. And the pion was actually discovered, but we'll come to that in a bit. So the pion was thought to be this particle that is exchanged between protons and neutrons, but it's not exchanged between electrons. For some reason, they don't exchange pions. The mass of the pion was estimated based on the range of the strong nuclear force. The pion has to survive long enough to exchange that force, but the pion cannot travel faster than the speed of light. So that means the pion must decay over time. And there are other particles that were discovered that decay over time. The more massive the particle is, the shorter its half-life. That's the time it takes for half of those particles to decay. So we'll talk about that in the next video. Right now, this is what the universe looks like. It's made out of this point in the video series. Protons, neutrons, electrons, neutrinos, virtual photons, we can throw that in, and also pions from 𝗟𝗶. In the next video, we're going to take a small tangent to talk about how we can use the range of the pion to estimate its mass.